Hello, George Romanic here. In today's video, we are going to investigate an interesting but rather challenging topic, and that's to find the probability of air atoms escaping gravitational pull of our atmosphere. To do that, we will have to combine two concepts in physics. One is the law of gravity, and the second is kinetic theory of gases. In today's video, we will use the law of gravity to find escape velocity from a planet. And then in the next video, we will combine it with kinetic theory of gases, from which we will borrow Maxwell-Boltzmann distribution of speeds in a gas to find the probability of an air atom escaping gravitational pull of our planet. I will carry out these calculations for Earth, but you can use the same concepts to apply it to Mars, Venus, or any other celestial object such as Moon. This theory that we will discuss in these two videos is very important because researchers can also use it as the first level approximation to understand the composition of an atmosphere of a celestial object. Using only this theory, you will be able to conclude that a body such as the Moon cannot have atmosphere because it has very low value of escape velocity. Whereas planets such as Earth, Venus, Mars, and so on can have an atmosphere because escape velocity is much higher. Well, what is this escape velocity to begin with, you might ask? Escape velocity is the velocity that any object needs to have to escape gravitational pull of a planet or any other celestial object. As we will see at the end of today's video, it's 11.2 kilometers per second for our beautiful planet Earth. Because this concept is so important and goes beyond the topic of these two videos, I will use three different ways to derive equation for escape velocity. I wanted to do it because the concept is so important, and my spiritual father, Richard Feynman, always said that a good theoretician needs to know several ways to get to the final theory or equation, if these ways exist. And here we can derive escape velocity using work energy theorem. We can do it using conservation of energy, and we can do it using the greatest law ever discovered, second Newton's law. Before we start, I would like to ask you to share this video with several enemies, perhaps even friends and family. Let us start by sketching this problem. Here we have our planet Earth, and it has radius RE. Radius of our planet, you should know that, is 6,371 kilometers, and let us say this is my radial axis R. As you can see at this point over here, R is equal radius of the Earth, RE. And then the axis continues, and eventually we will reach infinity. If I zoom in over here, I could make the following sketch. If this is that part of the surface of the Earth, imagine I take a rock and I throw that rock up. So axis R is going up like that, and I throw rock with some initial velocity v0 up. If this velocity v0 is smaller than the escape velocity, this object will just return to the ground. Because it is pulled down by gravity, and the gravitational acceleration is g, which is, 9.81 meter per second squared. In another circumstance, I can throw this object with higher value of initial velocity, and it will go further up, but eventually it will again fall down to the ground because of the gravitational pull of our planet. So velocity here, initial velocity, was again below escape velocity. However, there is a value of velocity v0 equals ve, escape velocity, that needs to be supplied to this object so that when we throw it up, it continues going up until it reaches in r equals infinity. When it reaches that point, it escaped gravitational pull of our planet and it will never again fall down to the surface. This is also important, we want to supply the initial value of velocity such that when the object reaches this point of infinity, it ends up with velocity v equals 0. That would be like having just enough fuel in your car to reach to the next gas station, and over there your car stops. This is the same case here. We provide initial velocity so that the object reaches infinity far away from the Earth, and then it stops there. Of course, if our initial velocity is higher than escape velocity, well, so be it. This object will just move even further away from our beautiful planet Earth. Now, to find this value of escape velocity, we can start by using the concept of work and work energy theorem. We know that work is equal integral of force as a vector times, or rather dot product, incremental distance dr between two limits, let's say r1 and r2. But because here we are interested in just one dimension, I can write this as a regular multiplication f dr. And what are the limits in this case? Well, that's simple. We start from the surface of the Earth, where r is equal radius of the Earth, and we need to go all the way to infinity, so the upper limit is infinity. Now, what is the force that is acting on our object as it is moving away from the planet? Well, that would be gravitational force, and we can express it using Newton's law of gravity as g m1 m2 divided by r squared, where m1 and m2 are masses of two objects between which we have gravitational force, and g is gravitational constant, 6.67 times 10 to power negative 11 meter cubed per kilogram per second squared. So if we plug in this force into this equation, we will get that work is equal. Now g is constant, m1 can be mass of our beautiful planet Earth, me, and m2 can be mass of this object that we threw away. Both are constants. And then we have integral dr over r squared, and the limits stay the same between radius of the Earth and infinity. Of course, this integral is very simple to solve. This is negative g me m and 1 over r, that's the solution of this basic integral, in the limits between re and infinity. And this is further equal g mass of the Earth times m with minus, and then here we have 1 over infinity minus 1 over re. 1 over infinity is 0, negative, and this negative will give me positive, so I will get that work A is equal g me times m divided by radius of the Earth. Now I would like to make a small mathematical note over here, because I know that mathematicians do not like when a person writes these indefinite integrals in this way. And there is a good reason for that. In principle, when you have integral, let's say in this case between re and infinity, you shouldn't write it like this. In principle, that integral should be written as integral between re and x, let's say, and then you put limit when x goes to infinity. That's what mathematicians like. So consequently, this solution would be, as you can see, A is equal negative g me m instead of this, I would have limit when x tends to infinity 1 over x minus 1 over RE. But this limit is simply 0, so I retrieve the correct result that A is equal G MEM over RE. Indeed, in atmospheric sciences and engineering and physics in general, we quite often can get away with this simple notation, but sometimes this evaluation of limit is incorrect and then we can end up in trouble. So it's always better to explicitly write it as a limit and then evaluate that limit. Okay, that was a mathematical note. Now going back to this result, this object needs energy to do work. You will remember from your high school physics that one of the definitions of energy is that energy is something that object needs to be able to do work. And I purposely said something because there are different forms of energy. There is potential energy, there is electrical energy, and there is kinetic energy. In the case of our object, we are interested in kinetic energy because object is moving. We need to associate escape velocity of this object with the work, and the energy of motion is kinetic energy. You know that kinetic energy is equal 1 over 2 mv squared. So you see, for this object to do work, to go from the surface of the Earth to infinity, it needs energy in the form of kinetic energy. And that kinetic energy needs to be equal this work A. So with this condition, I can write that 1 over 2 mv escape squared is equal this work G me m divided by radius of the Earth. Notice that masses of the object cancel, and from here we get this great and powerful result that the escape velocity is square root 2g me divided by re. Of course, you will remember from my video on gravitational force that we can introduce this constant small g that is universal gravitational constant times mass of the Earth divided by the radius of the Earth, and that is equal 9.81 meters per second squared. So I could also therefore write that the escape velocity is equal square root 2g small g re. Of course, here is squared. Now, if you plug in the values over here, you will get that the value of escape velocity for our planet Earth is 11.2 kilometers per second. Not meters, but kilometers per second. And that's very high velocity. 11 kilometers traversed every single second. That's the velocity any object, because as you can see, it's independent of mass, needs to have to escape gravitational pull of our beautiful planet and reach infinity. Now perhaps some of you are saying, interesting, but what about the case if the object is not at the surface of the Earth at the beginning, but it already has certain altitude, perhaps it's somewhere here? Then it should be easier to reach this infinity because it doesn't need to traverse this distance over here. That is correct, and we can easily account for that. If I say that A prime is the work that objects needs to do to go to infinity from a distance not re, but some re plus z, where z is this height over here, height from the surface of the Earth to that object's position. And then we again have force of gravity times dr, and then this becomes integral re plus z to infinity g mass of the Earth, mass of the object, divided by r squared dr. And then this becomes, well, that's the same integral as here. So if I plug in limits right away, I will get g m e times m divided by r e plus z. And then I have this same condition, but kinetic energy prime, let's say, needs to be work prime. So implementing this condition, one will get that 1 over 2 mv escape prime is equal g me times m divided by re plus z. Again, masses cancel. And if we rearrange this, we will get that ve is equal square root 2g me divided by radius of the Earth plus height of the object with respect to the Earth's surface. So, for example, if we now plug in the values of these constants in this equation and we choose z to be 420 kilometers, then we will get that the escape velocity in this case is 10.8 kilometers per second. So you see, from the surface of the Earth, it's 11.2 kilometers per second, but if you are already at 420 kilometers above the surface of the Earth, the value is 10.8 kilometers. So not a big difference. That's because our planet is huge and gravitational force is therefore very, very strong. But wait, some of you are saying, this makes no sense, because this particular height of 420 meters is the height of International Space Station. And I know from various online videos that astronauts in the International Space Station are weightless. So how is this possible? There is no gravity over there. In fact, gravity at the International Space Station is pretty much the same value as at the surface of the Earth. But there is another piece of physics that is happening there, and that's the following. I talked about it in my video on the orbit of satellites, so check that out. But here is the summary. You are standing here on the surface of the Earth and you throw your cat. You throw it horizontally, it travels some distance, then falls to the surface of the Earth. You throw your cat harder, it travels further and then falls to the surface of the Earth because of the gravity. You throw it even harder, it moves further and it will fall. And you can conclude from here, if you throw it fast enough, that cat or any other object like International Space Station will go around to hit you in the back of the head. And that's what is happening at the International Space Station. The station is moving fast enough so that as it is falling, the Earth underneath is also curving just at the right amount, so the space station will never fall to the surface. And therefore, there is a perception of no gravity at the station, when in fact there is gravity that is constantly pulling the station down, but the station is moving horizontally just at the right velocity to go around the Earth. Now let us derive escape velocity using conservation of energy. We can find our escape velocity using the conservation of energy. If here is our beautiful planet Earth with the radius RE, then we can say that position at the surface of the Earth is the so-called initial position of our object, and our object will be thrown towards infinity, which I will call the final position, and final position is infinity. The law of the conservation of energy says that potential energy at the initial position plus kinetic energy at the initial position needs to be potential energy at the final position plus kinetic energy at the final position of this object. Let us first discuss potential energy at the initial location. That potential energy is simply gravitational potential energy, and we know from high school physics that gravitational potential energy is G, mass of the Earth, mass of the object divided by the radius of the Earth. Now you might ask, why is gravitational potential energy negative? It is negative because our convention is to say that potential energy at infinity is zero. So to get a body from infinity to the surface of the Earth needs to do work, and therefore the object ends up having negative potential energy. That is just a convention that potential energy at infinity is zero. If, for example, people sat around green table and said potential energy at infinity is 333 joules for some reason, then for certain distance from infinity to our planet Earth, potential energy would be positive, and then again it would end up being negative. At any case, if you study physics, you will realize that really the value of energy has no real physical meaning. The most important is difference in energy between 2 points in time or 2 points in space and so on. Because energy always needs to be anchored to some reference value. And then that reference value is almost always arbitrary, which means that only the difference in energy states has physical meaning rather than the exact value. Well, during this discussion, I also told you that by definition, potential energy at F, which is infinity, is zero. So we covered this term as well. How about kinetic energy? Well, as I discussed on the previous page, if this is the surface of the Earth, we want to throw this object, so when it reaches infinity, final destination infinity, the velocity is equal to zero. It will just creep to infinity and stop there. So that means that kinetic energy at infinity will be zero. So we covered this term as well. How about kinetic energy at the initial location, which is Earth's surface? Well, that's the value of kinetic energy that the object needs to have to escape gravitational pull of the Earth, and that's 1/2 mass of the object times velocity squared. So as you can see from this equation, because this one is 0 and this one is 0, it ends up that potential energy at the initial location, which is the surface of the Earth, needs to be negative kinetic energy at the surface of the Earth. Well, that means now I substitute these. Negative G me times m is r divided by re is equal to negative 1/2 mve squared. M and m cancels, minus and minus cancels, and I get my beautiful formula that ve is equal square root 2g me divided by re. And again, the value is of course 11.2 kilometers per second. Now let us derive the escape velocity equation using the second Newton's law. Lastly, how do we get this result using Newton's law of gravity, the greatest law that we ever discovered? Here is the surface of the Earth, here is my radial distance r, the object is launched up, but the only force that is acting on it is gravity, Fgr. Mass times acceleration is the sum of all forces. But again, because this is 1D case, I don't have to bother with these vectors, so I can write that mass times acceleration in this radial direction is equal sum of all forces in the radial direction. But there is only one force, and that is gravity, so that means that mass times acceleration, I will write as dv dt, is equal force of gravity, but it is acting in the negative direction of my positive r-axis. Well, that means that m dv dt is equal negative force of gravity is g mass of the earth, mass of the object divided by r squared. Notice that masses again cancel. Now I will rewrite this term as delta v delta t plus v dv dr equals negative g me times m divided by r squared, but local change of velocity is 0. How to get from this derivative to local derivative plus advection? Check my video on advection. Now this is differential equation that separates variables clearly, so I will separate variables. v dv is equal negative g times me times m divided by r squared dr. And now I need to integrate this, so integral will again, as before, go from the radius of the earth to infinity, and here velocity will, so at the surface of the earth, velocity needs to be escape velocity. At the infinity, velocity reaches 0. So the solution of this is negative. This integral upon substituting these limits is negative ve squared over 2 is equal negative g me times m divided by r, but this r should also be negative, so I will get negative and negative give me positive. And then in the limits between r, e and infinity, so from here I get that negative ve squared over 2 is equal, upon substituting these limits, I will get here negative g over me times, sorry, there is no m here. I cancelled it everywhere here, so that's my mistake. gme divided by re. Now negative and negative will give me positive, so consequently I will get that ve is equal, once again, same result, 2g me divided by re. And that's the beautiful escape velocity from our planet Earth. Sorry for these few messy things, but as you know, I'm doing this more or less on fly, except for the value of some constants, so sometimes I do these mistakes. Escape velocity is also known as the second cosmic velocity. You might then ask, what is the first cosmic velocity? It's a velocity an object needs to have to be in a circular orbit around the planet. And I believe for planet Earth it is 7.9 kilometers per second, but you can double check online and let me know in the comment section if I was wrong. If the object has higher velocity than the first cosmic velocity, it will have elliptical orbit, and then if it has even higher velocity that reaches second cosmic velocity, namely escape velocity, it will escape gravitational pull of the parent planet. There is also third cosmic velocity, and that's the velocity an object needs to have to escape gravitational pull of the sun, namely to escape the solar system. And for our solar system, it's 42 kilometers per second. And then there is yet fourth cosmic velocity. What is that, you might ask? Well, that's the velocity an object needs to have to escape gravitational pull of the Milky Way galaxy, and it's around 320 kilometers per second for our galaxy. And there is also a fifth cosmic velocity. You might ask, what is that? Research is ongoing, but some researchers suggest that the fifth cosmic velocity is velocity that you develop when your girlfriend gives you a call and says she is alone at home, her parents left. Then the velocity that you develop running towards her home is known as the fifth cosmic velocity. There is still research going on, so if you have more insights into that, please let me know in the comment section below. I will see you in the next video when we will combine this escape velocity concept with Maxwell-Boltzmann distribution to find the probability of air atoms escaping gravitational pull of the Earth. See you there.